Hello, this talk will get more into topics from Phong lighting. We're going to first of all talk about all the inputs and all the outputs from Phong lighting, and then we'll do the formulas for ambient and diffuse illumination. All this can be found in Chapter 5 near the beginning, particularly Section 5.1. So Phong lighting, as I said before, this is a local lighting model, which means that we're going to consider light coming from a single light source, shining on a single point on a surface, being viewed by a viewer someplace, without worrying about whether there's other objects in the scene other than the light and the point that's being illuminated. We don't do anything with multiple reflections. We don't do anything with shadows. It's strictly, we assume there's just a light and a point that it's shining on and a viewer looking at it. All this stuff was developed by this person named Phong in a 1975 paper. Still a very interesting paper to read, although it's been quite a while ago. And this really set the groundwork for all of the local lighting models that are in use in one way or another. So let's talk about the inputs. So these are the things used to calculate Phong lighting. So the situation is, first of all, we've got a vertex is at position x, and x is a number in R3, or a vector in R3. Position x on a surface, S if it needs a name, with unit normal n. So what this means is we've got some surface S. At position x on it, there's a vertex, and there's the unit normal n pointing off of x at the surface at right angles to the surface. Okay, and the surface also has material properties, and so we think of the surface as made of some material, and it has properties that govern how it looks under light, mostly different kinds of colors. So here we have a lot of different material properties. So there's there's ambient reflectivity. We'll use the name rho sub A for this, but really this means it's a scalar, and it's the percentage of ambient light that's coming in that's reflected off the surface. But we'll have separate values for red, green, and blue. So it's really three numbers: rho A red, rho A green, rho A blue. And this is the Greek letter rho. And controls reflectivity of ambient. We'll have diffuse reflectivity coefficients. And this is the amount of diffuse light that's reflected. And these are called rho D red, rho D green, and rho D blue. The use of three colors is a little bit arbitrary, but it's common practice. It reflects the kind of color displays that we use and so forth, so it's very, very common. C is specular reflectivity. And this same kind of numbers controls the fraction of specular light that's reflected, and it's got red, green, and blue components as well. So rho sub S red, rho sub S green, rho sub S blue. And finally, there's emissive colors. These are not reflectivities. These are colors just actually generated. And so I stands for intensity. IE means emissive intensity. And there's the red component, the green component, and the blue component. So this is the amount of light just being emitted, say, by a glowing surface. There's also the specular exponent, or sometimes called the shininess coefficient, and this different letters get used, but I'll use F for the moment here. All these are scalars, so this is a total of 3, 6, 9, 12, 13 scalars that define the properties of the surface. Now this may seem like a lot, but to simplify things down a little bit, this is sort of the color of the surface. So the ambient diffuse values are usually the same color, or at least proportionally the same, in the sense that they're proportionally the same amount of red, green, and blue. They're usually control whether the surface looks some particular color. Does it look red? Does it look purple? Does it look magenta? Etc., etc., right? The specular reflectivity controls the specular highlights. Actually, the specular highlight colors. Now, this is usually a white or a gray, and we'll get into formulas for this in more details later on. And the specular exponent controls how shiny or glossy a surface looks, so I'll say glossiness. So this would be typically a number between, say, 10 to 200 range, sometimes smaller, sometimes larger, with a typical number might be like 80 or 100. It controls the size of those specular highlights, the little white shiny spots that we saw on surfaces in the previous lecture. And the emissive color is honestly not used all that often, but that's if you want to add in some extra color, just extra in addition to whatever the lighting model's given us. It's just a way to add in some extra color. So this is the first set of inputs. These are the inputs that give properties of the point that's being looked at on some particular surface. So the next set of inputs will be about lights, and I'll talk about those on the next board. So more inputs. First of all, 2 is light properties. And if there might be multiple lights, but we just consider one light at a time, and we'll just additively combine the contribution of color from all the lights. So the first light property is we're going to have a light position in space, or at least a light direction. So we may not give the light a position in space, but we give it a direction that it's shining from. And this is specified by a unit vector L, and L goes from the position on the surface towards the light position. So the picture is something like this. Here's our surface. Here's X sitting on the surface. Here's the normal vector, was a unit vector. Here's some light source. And it's a point light source. So we think of the light as being a single point, or having a single direction that it's shining from. And the L vector is a unit vector pointing from the position on the surface that's being illuminated towards the position of the light. So the light is shining this way, and we have some intensity of light, which will go, we have various names, but they all have I in, will be the intensity of incoming light. So in general, we'll have lots of I ins, but they all mean something about the intensity of the incoming light. So in is for incoming. Okay, and so that gives us the direction the light is shining from. And then we need the color of the lights. So we have various colors. So B, we have ambient incoming light. There's IA in, is ambient incoming light. And we're going to have 3 of them. There's going to be red, IA in green, and IA in blue. So the idea is, remember, we are splitting light into ambient, diffuse, and specular components. So the light is giving off some ambient component, which means that it's ambient means the light's not really coming from any particular source, but the point is, since a light is turned on, it generates ambient light throughout the whole scene. And so this measures how much ambient light throughout the whole scene is being generated by the light. And there's the red, green, and blue components of those. And then there's the diffuse light. So this is ID in. And again, this also has red, green, and blue components. So there's ID in red, ID in green, and ID in blue. And this is how much diffuse light there is. And we'll see what this means when we get to the formulas a little bit. But diffuse light means light coming from a particular light source, hitting a surface, and reflecting off equally in all directions. So that's the, and then we have, that's the diffuse component. And these are usually what we consider the usual, if a light has a color, if it's not just a white light, these give us the color. If it has a white light, it'll be equal components to red, green, and blue, because that gives us white or gray. There's also the specular component, I in S, and it's got green, red, and blue components. And this is the incoming specular light, and this controls how much the light generates specular highlights on surfaces. So again, we've got ambient, diffuse, and specular components of light. So these will make more sense once we have find the formulas for how to work with these things. And there's other inputs too. In particular, the light might have distance attenuation. It may get less bright the further you get from the light. It could have spotlight effects, etc. Okay. And then third input, we did the light properties and the surface properties now. The third input is the viewer position, or at least the direction to the viewer. So the viewer, let me draw my stylized eye as usual here. Here's an eyeball looking at the scene. And we have a vector vector v, I should say. Vector v is a unit vector. It's specified by a unit vector, v, pointing from x to the viewer. So this is a lot of inputs. We had quite a few. Was it 13 on the previous board? And here we've got a direction, a vector, 1, 2, 3, 4, 5, 6, 7, 8, 9, other scalar numbers for colors. So all in all, we're running, something like 25 different scalar values, plus, well, one more vector for the viewer position as well. So there's a lot of numbers that feed into this. So, good. So we will next talk about how we compute the response to the light. So far we've done the inputs. So we've got the position and the geometry of and the material properties of the point being illuminated. We've got the properties of the light source and the position of the viewer, or the direction of the viewer. And now we need to talk about what Phong lighting computes. And what its goal is to compute the brightness that the viewer sees at the point X due to the illumination by the light. So our goal is to compute the color, or the brightness, and brightness means like red, green, blue components, of the surface at X as illuminated by the light and viewed by the viewer, or seen by the viewer. And we'll talk about the ambient and diffuse parts of this on the next boards. So then the output of all this stuff is a I, which can be written as IA plus ID plus IS plus IE, is the the brightness of the surface as perceived by the viewer. So I is the color or brightness as perceived by the viewer. Okay. And actually, I wrote it just as one formula without any superscripts. But really, what I mean by this is there's an I red, an I green, and an I blue. So the viewer is seeing some amount of red mixed with some amount of green mixed with some amount of blue. And all these things measure the intensity of the light at that wavelength, or around that wavelength. And they add up to give us the overall color. Now, the calculations that we do are the same for each color. So frequently, I'm just going to start dropping the superscript red, green, blue, and it's understood that the formulas I give, they either apply to all the red components, or all the green components, or all the blue components. So what is this thing? So first of all, IE was an input. So as an input, there's nothing to compute, right? IA is the ambient light as seen by the viewer. So we maybe should have written superscript out there to go along with the in, but we simplified life by not writing that there. So our picture here is, here's our surface X, here's our surface, here's X, here's our viewer, and ambient light is coming from all directions. So we basically think of I in A is coming from all directions. And it hits this point, and it reflects out equally in all directions. So, and what is controlled here is we use the ambient reflectivity. IA is just defined to be equal to rho A times I in A. So there's a certain amount of incoming light that's labeled as ambient light. We multiply it by the reflectivity coefficient, rho A, for ambient light, and that'll be how much is reflected out. So trying to think of this as a physical thing, we're thinking of a certain amount of light's coming in from generally all directions. A certain amount of it's absorbed by the surface, and a certain amount of it is reflected off the surface and is visible. So what's happening physically here is that some of the light comes in and is absorbed by the surface, turns into heat there, vibrating molecules, and then is re-emitted as infrared light, which is not visible. So some of the light gets absorbed and then is eventually re-emitted as infrared, which isn't visible. Some of the light hits the surface and is bounced right off and heads off, however, in all directions. And that's what's seen. It hasn't changed its color. So this is the formula for IA. And IE was an input, so we've got it done also. So let's talk next about diffuse light. So diffuse light is going to have the following picture. Here's our surface with point X on it. Here's a viewer. And some light sources here. And it's sending light towards the surface at X. So there's some light coming in, I and D. As usual, we'll do this separately for red, green, and blue, but I'm just hiding that. Let me draw that standing upright a little bit better. And diffuse light is reflected equally in all directions. So it came in like that, and then it goes out equally bright looking in all directions. Okay. And of course, some of it goes towards the I position, and this will be the ID output as heads to the light. So here the formula gets a little more complicated, and I'll do that on the next board. So now we want to give the formula for the diffuse lighting. First, I'll redraw the geometry of the scene. we've got the surface S, point X on the surface, the unit normal N, the viewer is here, with a unit normal V pointing towards the viewer, and we're computing the intensity in this particular part of the presentation, intensity for the diffuse lighting. There's a light source here, there's the L vector, which is the unit vector towards the light source, and then there's the incoming light here. Again, we're thinking of the diffuse lighting. The diffuse component of this is computed by the following formula. I in D is rho D times cosine of theta times I in D, where theta is the angle between L and N. So this cosine factor reflects the fact that when the light comes in at a grazing angle, it's spread more widely over the surface, so there's less light hitting the surface per unit area, and so it's less brightly lit. To do this geometrically, let's draw this as a beam of light coming in towards the point X. Here's our light source, and think of a circular beam of light that's coming in towards the point X. And this circular beam of light, got a beam of light, and its cross-sectional area is equal to A. And so the intensity, I in D, this measures the light energy per unit area, or the number of photons per unit area of the beam, if you wish. When this beam of area A hits the surface, because it's coming in at an angle theta, it's elongated into an ellipse, and this multiplies the area by a factor of 1 over cosine of theta. So this area on the surface is equal to A divided by cosine of theta. So when theta is 0, cosine of theta is 1, so the beam is just coming straight onto the surface, so the circular cross-sectional area A of the beam is equal to the area on the surface. At an angle, cosine of theta is less than 1, so the area that the beam is hitting the surface is multiplied by the factor 1 over cosine of theta. What this means then is that the incoming diffuse light, I in D, is less intense per unit area on the surface than it is in the beam coming from the light source. This means that when the beam is hitting a surface from an angle, the surface is less brightly lit. And that's where this cosine of theta factor comes from. We can rewrite this in terms of vectors as rho D times L dot N times I in D. And this is because L and N are unit vectors, and the angle between them is theta, so L dot N is equal to cosine of theta. So a surface that obeys this kind of cosine theta rule is called Lambertian. So a Lambertian surface is a surface that obeys this type of formula. And most surfaces that you encounter in everyday life are Lambertian, or at least close to Lambertian. The name Lambertian comes from the name of the physicist Lambert. So ordinary objects that you see around you are, for the most part, Lambertian, and so they, for the most part, obey this rule. Not every surface is Lambertian, and the moon is a good example of something of a non-Lambertian surface. The moon, if you think of a full moon, the center of the full moon is facing the sun, so it's being illuminated directly on with theta equal to 0. The sides of the moon, as you're looking at it, are facing outward from the center of the moon, and therefore the sunlight is hitting them at a grazing angle. But our perception of the moon is that it's pretty much equally bright all the way across the surface of the moon. And so it's not Lambertian. This is due to the fact, something to do with the dust particles that make up the surface of the moon. It reflects light differently than a Lambertian surface. But apart from a few exceptions like that, many surfaces you see in everyday life are Lambertian. And therefore we use this formula for the diffuse lighting. Particularly the second one, because a dot product is a nicer thing to use than a trig function. So what we've done so far is we've expressed I, the intensity of the light heading towards the viewer, as a sum, IA, the ambient component, plus ID, the diffuse component, plus IS, the specular component, plus IE, the emissive value, which is attached to the surface as a material property. And we've shown how to compute IA and ID, and IE is one of the inputs. So what's left is how to compute IS, the specular component of the light, and that'll be covered in the next presentation. This is the end of this presentation. Thank you very much.